Now, as a natural expansion of Mohr circle for 2D problem, let's discuss about Mohr circle for strain in 3D. So here I will also skip the details, because you can take a look at in the textbook, and the mathematical structure is almost the same. So I don't want to bore you too much. But what I want to deliver is that for general strain state, that is composed of 6 independent components: epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, gamma zx. We are always guaranteed to find x prime, y prime, g prime axis such that there is no shear strain component. Okay, so for any arbitrary 6 independent strain component state, you are always guaranteed to find x prime, y prime, g prime coordinate such that there is no shear strain component. And after obtaining epsilon 1, epsilon 2, epsilon 3, three principal strain value, what you can do is you can draw Mohr circle for 3D using these 3 points, and you can draw Mohr circle for 3D problem. After completing this Mohr circle for 3D, we'll solve some example problem in the later part of today's lecture. And what you can do is, because the reading along the vertical direction is gamma over 2, the top point will be correspond to gamma maximum divided by 2, and gamma maximum divided by 2 will be same as the radius of Mohr circle, which is the maximum principal strain minus minimum principal strain divided by 2. Okay, and out of this equation, you can find that maximum shear strain, true maximum shearing strain, we are not considering like a 2D or in-plane shear strain. True shearing strain maximum value is same as epsilon maximum, the maximum principal strain, minus epsilon minimum principal strain. Okay, so please remember these little tiny detail, factor of 1 over 2, and you're not gonna make a mistake when predicting maximum shearing strain value. Then let me move on to the third topic of today's lectures right away, because we will solve example problem in separate section. So as a third topic, let me discuss about the relationship between Mohr circle for 3D stress and Mohr circle for strain. So until now, we learned Mohr circle for stress analysis and Mohr circle for strain analysis, and you may wonder like what will be the relationship between principal axis obtained from stress analysis and principal stress and principal axis obtained from strain analysis. The answer is, and to get the answer, you have to get to the basics. Okay, so let's go back to the basics. So we learn about like a generalized Hooke's law in chapter 1 and 2, and here what we have learned was following. So when we have some coordinate system x, y, z, and suppose that we measure 6 stress component and 6 strain component, and we discuss about the relationship between strain and stress. Okay, here what we have learned is that the normal strain and normal stress component, they are coupled to each other. When you have like a sigma x and sigma y and sigma z, they affect the other strain component too. Even though you have sigma x that is non-zero and sigma y 0 and sigma z 0, what you realize is that even though sigma y and sigma z value is 0 and 0, if you have non-zero sigma x, due to the Poisson ratio, you can have non-zero epsilon y and non-zero epsilon z, even though sigma z and sigma z are 0. Okay, so this is the case for the normal strain and normal stress. But what you have found here is that gamma xy and tau xy, and gamma xyz and tau yz, gamma zx and tau zx, they are only connected to each other and they don't have any crosstalk, right? So when you have this strain component, you don't need to worry about like other strain component like a tau yz and tau zx do not affect gamma xy. Okay, in this case, what's the definition of a principal axis? When you have principal axis, it means that if you have principal axis for stress, there is no tau value. Tau xy, tau yz, and tau zx is 0, and it directly implies that when 3 of these components are 0, these 3 components are automatically 0. Okay, so due to their simple material relationship. Okay, so here what you can realize is is that, of course, in the other way, when you have an axis where gamma xy and gamma yz and gamma zx are all 0, yeah, your axis is guaranteed to have 3 shear stress to be 0. Okay, so the implication here is that this guy is equivalent to that guy. 0 shear strain is equivalent to 0 shear stress, and it means that principal axis should be identical for stress analysis and strain analysis. Okay, so if you obtain the principal axis from strain analysis problem, then it should be a principal axis for stress problem too. Okay, so this is something you have to memorize when you have to connect two analysis. Okay, so some problem ask you stress questions after giving you strain information. Some problem would give you stress information and ask you strain problem, and you have to get the answer on whatever problem is given. And one of the most important thing you have to remember is this fact: strain principal axis should be identical. Okay, so with that, let me finish the this video lecture. The video lecture is for topic 2 and topic 3.